a complex number is written in the form a plus iota b, where a and b are real numbers and iota is the imaginary unit such that iota squared equals -1. The number a is called the real part, written as Re of z, and the number b is called the imaginary part, written as Im of z. Complex numbers are especially useful because they solve equations that have no real solutions, such as x to the power 2 plus 1 equals 0. For example, z equals to plus 3 iota or z equals -1 plus 4 iota. The addition of complex numbers is done by adding their real and imaginary parts separately. For example, open bracket 2 plus iota 3 close bracket plus open bracket 4 minus iota 5 close bracket equals 6 minus iota 2. Addition works by combining real parts and imaginary parts separately. If z1 equals a plus iota b and z2 equals c plus iota d, then z1 plus z2 equals open bracket a plus c close bracket plus iota times open bracket b plus d close bracket. For example, open bracket 2 plus iota 3 close bracket plus open bracket -6 plus iota 5 close bracket equals -4 plus iota 8. Subtraction is similar. We write z1 minus z2 equals open bracket a minus c close bracket plus iota times open bracket b minus d close bracket. For example, open bracket 6 plus 3 iota close bracket minus open bracket 2 minus iota close bracket equals 4 plus 4 iota. Addition and subtraction are closed, commutative, and associative in the system of complex numbers. Multiplication is also straightforward. If z1 equals a plus iota b and z2 equals c plus iota d, their product is z1 times z2 equals open bracket a c minus b d close bracket plus iota times open bracket a d plus b c close bracket. For example, open bracket 3 plus iota 5 close bracket multiplied by open bracket 2 plus iota 6 close bracket equals open bracket 3 times 2 minus 5 times 6 close bracket plus iota times open bracket 3 times 6 plus 5 times 2 close bracket. That simplifies to -24 plus iota 28. Multiplication is closed, commutative, and associative, and has a multiplicative identity, which is 1 plus iota 0. For every non-zero complex number, there also exists a multiplicative inverse. If z equals a plus iota b, then the inverse of z is a minus iota b divided by a squared plus b squared. To divide to complex numbers, we multiply both numerator and denominator by the conjugate of the denominator. If z1 equals a plus iota b and z2 equals c plus iota d, with z2 not equal to 0, then z1 divided by z2 equals open bracket a plus iota b times c minus iota d close bracket divided by open bracket c squared plus d squared. For example, let z1 equal 6 plus 3 iota and z2 equal to minus iota. We compute open bracket 6 plus 3 iota close bracket divided by open bracket 2 minus iota close bracket equals open bracket 6 plus 3 iota times open bracket 2 plus iota close bracket divided by 5. That expands to 15 plus 12 iota divided by 5, which equals 3 plus 2.4 iota. This method ensures that the denominator becomes a real number and the result is always expressed in standard form. Powers of iota follow a cycle that repeats every 4 steps. Iota to the power 1 equals iota. Iota to the power 2 equals -1. Iota to the power 3 equals negative iota. Iota to the power 4 equals 1. Then the cycle repeats. This means iota to the power n equals iota to the power n modulo 4. For example, iota to the power 5 equals iota to the power 1, which is iota. Iota to the power 6 equals iota squared, which is -1. iota to the power 7 equals iota cubed, which is negative iota. And iota to the power 8 equals iota to the power 4, which is 1. This repeating pattern helps us simplify many algebraic expressions involving complex numbers. Let's recap the algebra of complex numbers. We defined a complex number as a plus iota b. We learned how to add, subtract, multiply, and divide them. We also explored the powers of iota and saw how they follow a repeating cycle. Complex numbers help us solve equations that have no real solutions, like x squared plus 1 equals 0. The properties of closure, commutativity, and associativity make complex numbers behave consistently under algebraic operations. Finally, complex numbers are not only theoretical, they are widely applied in mathematics, physics, and engineering, making them an essential part of higher studies.